Hey, good morning to you, or whatever time of day it is you're watching this video, from the North Platte River here in southern Wyoming. I'm just a few miles north of the town of Sinclair, which is an interesting story in itself. Maybe I'll do a video on that. What's a day without looking at another mystery outcrop, you might be asking yourself. I don't know, so here I am again, looking at another mystery outcrop. In this case, it's a sandstone that's caused a lot of confusion, a lot of debates, some arguments, friendships have been lost. It's a saga, and we're going to get into it in just a second. It's first thing in the morning here. Sun just came up about 45 minutes or an hour ago. This outcrop serves as a great reminder of how important lighting is, especially if you're leading field trips. You know, it's really frustrating sometimes when you plan a perfect field trip with all the stops and time everything out, and then you realize, oh no, this is a eastward facing outcrop, and when you show up in the afternoon, this whole thing is in shadow. It makes it really hard. That's the beauty of doing video field trips like this, is I can come out during the best part of the day, video these things in the best light, and share them with anybody who wants to see. But enough about that. Like I mentioned, we're in the North Platte River in an area called the Dugway, north of Sinclair, Wyoming. And I'm looking at the Mesa Verde group. So this sand behind me is the first thick sandstone in the big clastic Cretaceous succession of the Mesa Verde, which started prograding from west to east at about 80 million years, give or take a few million. So it's late Santonian through Campanian, right up until the Maastrichtian at the top. The Lewis Shale was a big transgressive deep water shale unit that came on top of the Mesa Verde before the Medicine Bow and Lance equivalent clastic wedge started building out. So this is a Campanian, largely succession of clastic shallow marine deposits. That part's not controversial. The controversial part is, what were the sedimentary processes and the paleogeographies that led to creation of outcrops like this, sandstone bodies like this one? There's a few more up the canyon, like Seminoes 1 and 2, the tongues. There's the Allen Ridge Formation, there's the Almond Formation. We're going to cover those in a separate video. This one I'm going to focus exclusively on this very first big thick sandstone body because it's been the most contentious. It's the O'Brien Springs Sandstone. I thought I would run through the main depositional models. As I mentioned, it's the first of the big sandstone bodies of the Mesa Verde group, and it forms a nice big prominent ridge that you can follow for miles and miles and miles. You can get some really good cross-sectional views of this thing as it goes out into the basin. There's a very real question as to whether it was prograding to the east, to the south, some combination thereof. So we'll talk a little bit about that later on in the video. But the main depositional models for this thing were starting in the 80s, 60s, 70s, into the 80s, that it was an offshore shelf sand. And it's really interesting because back in the 70s, 80s, even early 90s, there was a lot of discussion about shelfal currents and reworking of sand and sediment on the shelf. That sort of was dropped by the 90s, and certainly by the late 90s into the 2000s, when sequence stratigraphy took over. And sequence stratigraphy heavily relies on changes in sea level, base level, proximal distal changes. And a lot of these shelf sands were reinterpreted as low stand deltas that got reworked by shelfal processes. So the idea of shelfal currents and shelfal reworking of sediment sort of was shown the door in the 90s and 2000s. People didn't want to talk about it. With renewed interest in oceanographic research and studies of modern systems, we realized shelfal currents, not just shelfal currents, but bottom currents in general, in the deep water, on the slope, in the abyss, they're very significant. Now, submarine captains and submariner types have known this for decades. Laying cable across the Atlantic, people knew this. Somehow geologists were a little bit slow. It took us a while to catch on. So these things went from being interpreted as shelf sands in the 80s to low stand deltas in the 90s. Then there was kind of a resurgence of interest in the 2000s, the 10s, the teens, and especially now. So the current model that me and some of my colleagues are working on is that these things really are shelf deposits, but there's a catch. They're actually reworked sand from an uplift to the north. So there was a paleobathymetric high. We're in a tectonically very active basin. Paleobathymetry would have created these high spots on the ocean bottom, and with these bottom currents constantly flowing from north to south, they would have eroded anything that's being uplifted and redeposited that material as soon as they reached lower energy area, and there just happens to be an uplift to the north. It's called the Granite Mountains, and it's been active throughout the Cretaceous into the Paleocene and Eocene. It finally collapsed not long ago, about 8 to 10 million years ago. But the Granite Mountains uplift probably was the source for these sands that were getting truncated by bottom currents and then redeposited. At least that's our idea right now. Check back with me in a year or two, might have changed. But that's enough gabbing about models and hypotheses. Let's go actually look at some rocks. That's what we're here to do. So I'm going to walk you through, as usual, bottom to top. Look at the sedimentology, the stratigraphy, the ichnology. They all tell us some really important things about how this sandstone came to be. Before we run across and start sticking our nose right up against the rock and recording observations, it's always good to do an initial walkthrough or a flyby just to get the feel for the outcrop. A guy I used to work with called it getting the karma of the outcrop. And it's a really good idea because it kind of gives you an overview before you start getting into the nitty gritty. Looking at the forest before you start counting the trees, right? Right off the bat, you notice there's two sections here. There's this lower section that has a little bit of a lower angle slope to it. And it seems a little bit darker in color. And then there's this surface that seems to run through. Then there's an upper part of the outcrop, which is lighter colored, maybe more regularly bedded. If we're going to be bold and say lithology is the cause of this bedding, then you might say the lighter color is sand, the darker color maybe has some more muds or silts or clays in it. So we've got two parts of this outcrop at least, one lower, one upper, differences in bedding, possibly differences in lithology. That might be telling us something important about the environment. A lot of times people point out that it seems to be shoaling upward, it seems to be coarsening and thickening and cleaning upward, but very many people take a look at this and say, shore face. But we're not going to do that. I think it's something else. All right, we are in the lower part of the section, this kind of grayer material, and once again, low light is our friend. These are talus blocks that have come down from somewhere up above, but there's a lot of information on them. You can see in this one, there's ripples, there's lingoid ripples. Now, that's an interesting observation because we're not seeing a lot of really strong hummocky or swaley cross stratification, which is common in storm-dominated, wave-dominated successions like a shore face. This is just one block, but looking around, it seems like an awful lot of these blocks have these lingoid ripples or sinuous crested ripples. They're called lingoid because they kind of look like a tongue was working on, like a cat was kind of licking, going blah, 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 blah. And it creates that kind of lingoid surface. Looking around, trying to find some outcrop that's in place, not displaced in talus blocks, and sure enough, here's little bits of it peeking out. There's a lot of wavy bedding, some flasier bedding. Flasiers are just ripples that have mud drapes, kind of partly separating out the individual sand layers. So there's a scheme of wavy, lenticular, and flasier bedding, which basically accounts for the amount of mud versus clay in the system. There's actually a combination of wavy, lenticular, and flasier bedding in here, and that tells us there's oscillating currents. Stronger, weaker, stronger, weaker. That can form in a lot of environments. It happens in fluvial systems with episodic flows. It happens in tidal systems. It happens anywhere you have fluctuating energy. Not very common in a wave-dominated, storm-dominated succession like a shore face, though. So that's another interesting observation here. Here's another rippled sandstone that has a texture reminiscent of some of the microbial mats we've seen in various environments. Sort of a rugose, almost like a little carpeted texture. That could be partly bioturbation. It looks like there's little tiny burrows that might be things like chondrites or helminthopsis, tiny little burrows. But it could also be those guys in combination with microbial mats. So again, telling us that there's light penetration, water's probably pretty warm. This could be from the shallower part of the succession. All right, now we're talking. So here's a sort of rippled surface. It's really hard to tell. They're very slight, very faint, but it looks like there's a little bit of that lingoidal ripple surface to it. But look at this. Big, smooth lined burrows all throughout. These are thalassinoides, made by a variety of organisms, usually considered to be made by shrimp, kaolin acid shrimp, but polychaete worms make them, all sorts of other marine animals make them. They've got that smooth lining, because the sand was consolidated. If they needed to consolidate it in a loose sand, they would make little pellets and it would be called ophiomorpha. But we've got some large marine organisms living in amongst this rippled sand that has a surface that looks a lot like microbial matting. Again, nothing hummocky or swaley or storm or wave dominated looking in this. Here's another block. We're looking at a cross-sectional view. You can see the bedding in there. But take a look at this. There's a big thalassinoides burrow in cross-section. There's a couple of smaller ones side by side. Hard to tell. That could be a single rhizocorallium with two tubes. It could just happen to be a couple of burrows side by side. But look at this little guy. That is Ichnology. And Ichnology is a horizontal burrow where the animals come down, burrowed, then adjusted upward and burrowed, and adjusted upward and adjusted upward and adjusted upward. So this burrow at the top is the last one. This one's the first, but it creates a series of little smiles in cross-section. That's Ichnology, very common in marine and brackish water settings. So we've got big crustaceans or polychaetes. We've got Ichnology, which could be made by crustaceans or polychaetes. A variety of animals make both. Interesting. Check out this bioturbated surface. These little guys are very common in tidal systems. I've seen them in the Jurassic. I've seen them in a lot of Cretaceous systems. They're very, very common. They almost look like teeny tiny little rhizocoralliums, but they're not. But their presence here, again, is consistent with a sort of lower energy, not high energy storm or wave dominated setting. And again, this is a talus block that came from up there, but it definitely has come from this grayer interval, not from the lighter interval. So we're going to keep walking through. A lot of times surfaces like this are best seen on talus blocks because the stuff that's in place, this is in place, and you can see it's covered up with talus. The talus has all kinds of great trace fossils in it. So does the stuff in place, but the in place material, unless it's been cleared off by a road cut, can be kind of hard to see. So looking around a little bit more at the talus blocks, here's another great example of heterolithic lithology, where there's a cleaner, thicker sand down here. Then there's a break, and there's a much more heterolithic succession up here. So it's sand, silty mud, sand, silty mud, sand, silty mud stacking up. And you can see there's some really cleaner sandy bits. The grains jump out, and then there's the siltier, muddier bits. This is wavy to lenticular bedding. So again, typical of oscillating currents, common in tidal environments, not terribly common in storm-dominated deposits. We've been walking through and still have not seen anything that looks like a definitive storm wave deposit. Here's another cool surface exposure of sort of rippled sand, but there's a surface trace called gyrocorte here, and it's got a central groove with two little lobes on either side and then scratch marks. You know, it could also be a type of Cruziana. They're very similar. But the point is, it's probably a little isopod crawling around on the seafloor. There's also, you see these smoother, more arcuate traces. There's evidence of some little vertical guys. There's our little bitty squiggly friends again. So not a super rich ichnofauna. Talk about bioturbation. This is a heavily burrowed surface made up of big thalassinoides, smaller paleophycus, looks like maybe some Scolithos or Planolides. Very simple horizontal or vertical burrows, nothing intricate, no really complex feeding or dwelling structures like you would expect in an open marine setting, but common in an environment where there's enough salinity and nutrients to keep shrimp and worms happy. But not a lot of more complicated things, not things like Asterosoma and whatnot. Over here on the next block over, look at that. Here's our friend Gyrocorte again. There's a variety of other horizontal traces, some simple vertical traces. Not a lot of diversity though. So we're kind of seeing the same things over and over. Hey, look at that. That is a big ophiomorpha in the making. You can see the knobbles on the side. See those pellets? This one's not very convincing, but we're gonna look around and see if we can find some more. Because again, thalassinoides made by shrimp. There we go, that's maybe another wall of an ophiomorpha. Thalassinoides is made by shrimp when it's consolidated sand. If that sand is unconsolidated, they have to reinforce it with pellets and make ophiomorpha. So let's see if we can find some more. Oh boy, did we find another one. Take a look at this beauty. This is a three-dimensional cast of an ophiomorpha. So you can see the pelleted wall right there. It's used little round pellets made with agglutinated mucus that they secrete. Take sand, mucus together, make a little ball, and align the burrow wall to prevent it from collapsing on you. But in this case, the burrow, after it was abandoned, got filled in by sand and made a natural cast of the ophiomorpha. So you can see the wall, you can see the natural cast, and the little shrimp, because it's calcium acid shrimp that make the pelleted lining. Polychaete worms don't do that, calcium acids do. And the little guy that lived in here was probably pretty small. By analogy, the ones that I found on the Texas Gulf Coast that make a burrow about this big are generally only about maybe an inch, inch and a half long, 2 centimeters long. So they're little bitty guys. Ghost shrimp, they're called. People use them for bait. Poor little things. Okay, so we walked up through that grayer interval. We're pretty much to the top of it up here. And then we get to that lighter colored sandy interval. We'll take a look around the corner. Man, that is a lot of bird poop on this. This is a popular place with raptors. We're going to take a look at the tippy top of the grayish interval, which so far has indications of oscillating currents. The trace fossil assemblage is marine, but not really robust and diverse marine. There's a lot of burrows on some surfaces. Many are devoid of burrows. So all this is indicating a fairly stressed environment. Very possibly a tidal system. And here I am at the top of that lower succession, and wow, you can see there's some real discrete packaging here. Looks very rhythmic. We've got some thicker sands, then some heterolithic sands. Thicker sands, heterolithic sands, thicker, and so on and so forth. None of these sands have anything indicating wave-generated structures. In fact, they're all fairly laminated, maybe with some wavy or undulatory bedding. Burrowing is not super abundant. There's not a lot of burrowing in these bodies. So I'm going to say, and my co-authors and previous authors, this is nothing new, have all agreed that this lower part is a tidal sand. Whether it's a shelf tidal sand or a low stand tidal delta, there's been the debate. We're leaning towards it being a shelf tidal sand. And we can talk about that more. I already mentioned the uplift to the north. I'm not sure how much more there is to say. I'll put a link to the paper in the description so you can download it yourself and have a laugh if you think we're totally out to lunch. Next up, we're going to look at the upper part of this succession, because maybe something's changed. Maybe that upper part, which is lighter sand, it looks maybe more massive towards the top. Maybe that's very different than this lower part, which seems to have a lot of mud and silt, giving it that grayer color. Wow, there's a significant change here. This is the contact. This is the surface between that lower dark gray tidal sand and this upper cleaner sand. Woo! I'm going to try not to fall down the cliff onto the highway. It'd make for a great video. Bad day for me. I got my orange shirt on though, so any trucks that are coming along would see me, so that's nice. But look at this bioturbated surface. That is heavily, heavily chewed up, consistent with this thing having been transgressed. So the lower sand might have stopped building out long enough that whatever the sediment deposit system was, whatever the delivery system bringing sediment and maybe fresh water or whatever else, it turned off long enough. It might have just been an energy thing. If there was just enough sediment chugging along to kind of hinder development of a benthic fauna, and then that sediment supply kind of stopped, it would be immediately colonized by organisms like this, all the worms and shrimp. So we're going to take a look at that more consolidated section up there, and then I'll show you what's in the sand right there. That is very exciting stuff. Wow, super robust and healthy ophiomorpha all throughout here. That's telling us that the stress that was kind of hindering traces down below has been alleviated. And we've got some healthy bottom fauna. So it's a little bit tricky to climb on that. I'm not going to do that. It's really flaky, but you can see it's got a sort of undulatory surface. There's a fair amount of burrowing on it, not as much as immediately below. So in that gray section with the big ophiomorphas and big healthy traces, that's probably the transgressive surface, the flooding surface. So here we are on the lower part of that upper sand, and oh my goodness, very, very different. Look at this cross-bedding. Big cross beds. The full sandstone bed is a single cross-bedded unit going roughly from northeast to southwest. So it's kind of dipping in that direction. The one below has some little ripples at the top and cross-bedding going the opposite direction. So that cross-bedding is actually going from southwest to northeast. And then there's little ripples at the top going northeast to southwest. That's curious. Bidirectionality in this bed. The beds above seem to have a stronger northeast to southwest flow. So we've got a couple of different modes of deposition here. One is something from the northeast, delivering sand to the southwest. But then there's also episodes of deposition from southwest to northeast. That sounds a lot like a tidal system to me. And you know, not surprisingly, in these big cross-bedded sands, there's not a lot of burrowing. You know, it's high energy deposit. There's not a lot of things that like living in sand like this, and they're deposited so quickly that nothing can really colonize these surfaces. When that deposition stops and you get the kind of finer grain muds and silts, that's when organisms can colonize. And sure enough, it's chock full of simple tubular burrows like Paleophycus, the Elasinoides, and so on in here. And then we get another deposit of high energy sand screaming in, and then it shuts off, and so on and so on. So we're seeing high energy deposition of cross-bedded sand, then it shuts off, happy burrowing animals. High energy deposition of sand, shuts off. You know, again, not exclusive to tidal systems, but the fact that this is all cross-bedded and not hummocky or swaley, no wave-generated structures, no storm-dominated structures, it's all bottom traction current features. It sounds a lot like bottom currents are the culprit. Whether they're tidal or not, it looks a lot like we've got strong bottom currents, unidirectional, sometimes bidirectional, but not orbitals like you would expect in storm-dominated sections. Yeah, and looking at these finer grain intervals, take a look at the large Elasinoides. So when the system isn't depositing sand, it's healthy and robust. There's some nice big shrimp, there's lots of organisms living here, but as soon as that sand turns on and starts depositing, they don't like it. In this case, these burrows are filled in with sand, so these animals live in their burrows for, you know, a number of years. Elasinoides is made by kaolin acid shrimp, and that's their dwelling structure. They live in there for years. They don't just dig them and run to the next spot and dig another one. So this is indicating there's probably a significant amount of time between them occupying this burrow and it getting filled in with sand. Now, how much of that time is missing because this sand came through and truncated and redeposited, we really can't say. But it does give you the feeling that there's a significant amount of time here in this fine grain interval between periods of sand delivery. So, you know, was it every couple of years? Could be, a couple of decades, possibly. It's stacked up, like really sandwiched in here. Look at that, just boom, 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 boom. So it's fairly continuous deposition, but it looks like it was breaks in between. We used to call this lamb scram, laminated and scrambled. I don't know if people today still call it that. It might be a relic from the 80s and 90s, but this is pretty classic lamb scram. Ripples, more ripples. Look at that, beautiful ones. Sinuous crests, not quite linguoid. Not a lot of burrowing. There's some little through-going horizontal traces, but not a lot of big, healthy ones. There's even what looks like maybe some plant material. We'll keep looking around. I know I've found chunks of wood and chunks of palm fronds in some of this stuff. More sinuous crested ripples, complete with plant stem fragment here. And it looks like maybe a couple more plant stem fragments, but for sure straight to sinuous crested ripples. Beautiful, beautiful. They're darker in color, probably because there's a little bit more organic material in this interval. Oh, speaking of which, look at that. That is a clast of shale. That's a rip-up clast of shale. So that's mudstone that got reworked from somewhere and dumped into this cross-bedded sand. That's typical of tidal environments. The mudstones are generally pretty resistant to weathering and are rubbery and form these kind of elongated, rounded clasts. Look at this, more rip-up clasts of mudstone that have been flattened in the cross-bedding. We're looking at a cross-sectional view, and this is really, really typical of tidal systems. So I'm walking along through the rest of the succession to the top, because after a while it gets pretty monotonous. It's cross-bedded sand. In this case, we're starting to get some big hematite or siderite concretions in the sand. That's indicating porosity and permeability that allowed ironstone concretions to form after the groundwater was percolating through the sand and concentrating that iron oxide in these zones of higher porosity, higher permeability, destroying them. Incidentally, in a bunch of hydrocarbon reservoirs, this is a problem. If you're trying to drill through these things, you can see those nice big vertical drill bore holes from when they were blasting for the highway. If you're drilling and hit some of these things, that can cause a lot of problems in a hydrocarbon reservoir, or carbon, or carbon storage reservoir, anything like that. But the sand is getting thicker and thicker and thicker, and more cross-bedded through here. There's a lot of bidirectionality in some of these beds, indicating currents going back and forth. So putting that all together, we're seeing bidirectionality, we're seeing oscillating currents. None of these is 100% unique to tidal systems, but considering the physiography of this basin, we're in a setting where up to the north, there's a big major mountain uplift. Down to the south, there's the Sierra Madre and Medicine Bows that are uplifting. So we're in a basin that's got these kind of tectonic highs creating effectively tidal straits. In the Western Interior Seaway, all it would take was some uplifts surrounding an open area to create a perfect tidal strait. There's also evidence for uplift to the east in the Simpson Ridge area, maybe the Laramie Mountains. There's a lot rocking and rolling here. The Rawlins uplift is immediately to my west. So the bottom's moving, so we've got a fair amount of paleobathymetry available to create all kinds of funky tidal currents. Combine that with bottom currents, shelfal currents that were coming from the north to the south, and you've got optimal conditions for creating a sandstone body like this. It's not a delta, it's not a low stand delta, it's not just some shelf sand that was somehow out there fed by deltas. So we've got a strongly bottom current dominated deposit with an overprint of tidal influence. That's kind of cool. I jumped across the highway to give you a better view of this upper part of the section. And you can really see those concretionary zones in there, but you can also see how really sand dominated this section is up here. We've lost the heterogeneity from down below. It's just all sand on sand on sand in here. And here we are, back to the start. Just to do a little bit of a recap, in case you fell asleep or you skipped ahead because you don't feel like being bored out of your skull looking at the minutiae of sedimentology and ichnology. I can't imagine why. We looked at two sandstone bodies that make up the O'Brien Springs member of the Haystack Mountains Formation. The lower one is this darker gray, very fine-grained heterolithic, low bioturbation intensity, low diversity package of sand. It's got features that look a lot like tidal current deposits. We've got wavy and undulatory and flasier bedding. We've got a lot of ripples, no big strong cross beds, nothing indicating high energy. It's all fairly low energy. Low diversity assemblage suggests a stressed marine environment. That could be because of high sedimentation rates, could be because of low oxygen, decreased salinity. In this case, it's probably high sedimentation rates. Then there's a transgressive surface between the two with big, happy, robust ophiomorpha, lots of burrowing. That suggests this lower sand stopped deposition long enough for semi-normal marine conditions to resume. Happy burrowers came in, they're doing their thing, and then wham, into this really strongly cross-bedded, very sand-rich and increasingly so body. So we have heterogeneity down here, we had lamb scram, strong cross-bedding. Some of it has bidirectionality. Most of it's going from the northeast to the southwest, but there's also a component of southwest to northeast, suggesting currents going in two directions. As we worked our way up to the top, we saw the fine-grained material gives way to sand on sand on sand, and even some concretions. Big siderite, maybe hematite or anchorite. I haven't done the mineralogy. We always just call them siderite concretions out here, so I'm going to trust previous authorities on that. That never gets you in trouble. And then finally, we're in very tall, very high cross beds. These things are up to meter scale, suggesting high energy at the crest of a paleobathymetric high spot, this sandstone body. So wrapping it all up, there's really good evidence here that we're in a tidal strait. We're surrounded by laramide uplifts. No indication of storm or wave dominated deposits, no hummocks, no swales, no nothing like that. I think we can put this one pretty much on the shelf of we're in a bottom current dominated, tidally influenced shelfal sandstone body that was deposited in a strait. And hey, as always, thank you very much for watching. I really appreciate it. Now I'm going to continue on my journey up the canyon, see what else we see in there, and I'm going to keep making these videos. I hope you'll keep watching. I'll see you next time.